Okay,
Yes.
okay, let me start. So we are very happy to have Dr. Luca Calatroni as the speaker today. Luca is one of the organizers that many of you know. He's a CNRS junior research scientist working at the I3S laboratory of Sophia Antipolis, France since 2019. He got his PhD in 2015 from the University of Cambridge. And after that, he has been a Marie Curie postdoc at the University of Geneva till 2016 and a lecturer Adm research fellow at the Applied Mathematics Center of the École Polytechnique in France till 2019. His research focused on the mathematical modeling of inverse imaging problems where variational and evolution models and on the design of numerical optimization algorithms for their efficient numerical solutions. With application to biomedical imaging, digital restoration of artworks, and vision. And today, Luca will talk about on and beyond total variation, regularization in imaging, the role of space variance. Luca, it's your talk now.
Thank you very much, Raymond. Thank you very much also to all the other organizers who invited me to present my work in this seminar series that has now been running since 1 year almost. So I'm very honored to be part of the speakers in this seminar series. And today I will be presenting you some recent work on some specific aspects of the use of total variation regularization in image restoration and reconstruction. And in particular, we will focus on the aspect of space variance, which has been studied and explored by different communities under different names. Let me say that this is a joint work with a few collaborators from the University of Bologna, Monica Pragliola, Alessandro Lanza, and Fiorella Sgallari. And among them, I really want to acknowledge and to highlight the contribution of Monica Pragliola, since this is highly based on her PhD thesis, on which I had the pleasure to collaborate over the last couple of years. So I start with a very soft and probably obvious to most of you introduction, just to fix the notation and providing some context. So we are thinking of a standard linear inverse problem when where we observe a given noisy, blurred, and possibly undersampled image F, and what we seek is an image U, which is linked to F through these linear inverse problems where K is the supposedly known linear operator modeling blur and undersampling, while E is an additive noise realization. So I don't specify here what is the type of noise that we consider. I will talk about that in the following, but for the moment, let's simplify and just say that is an additive noise component. So as we know, computing a solution of this problem in this form is a nilpotent inverse problem, and so we typically look for approximation of solution, so reconstructions that we will call U stars. And what I will define in the following are the two probably most considered paradigms to solve these nilpotent inverse problems. Of course, there are many more, but for what follows, I think we'll focus on these two mostly. The first one is the statistical paradigma, where the idea is to solve this problem by modeling the different ingredients, in particular U and F, in terms of their probability density function. In particular, so one can then define a solution U star as the maximizer of the posterior probability, which by standard application of the Bayes formula can be expressed in this way, where we see different contributions. The first one, which is color-coded in orange, would be referred to as a prior distribution, which encodes prior beliefs, prior information we're supposed to have on the solution U, whereas the second one, the red one, is the likelihood function, whose form typically describes noise statistics. So from this context, we can alternatively consider a more optimization-related point of view to solve this problem by taking first the negative logarithm of this product, neglecting the constant depending on f, which does not involve the minimization variable, and then assuming some form both on the prior and on the likelihood function, in particular some negative exponential form, depending on two functionals which are called R and phi. The first one typically referred to as regularization term, and the second one fidelity term. So those have and play the same role as prior and likelihood functions, but from a variational point of view. So this is the standard minimization problem we often encounter in many imaging applications, so that it can be studied and analyze both from a variational viewpoint, or also by taking some derivatives in appropriate senses by looking at evolution models. So for instance, inspired by PDEs and so on and so forth. So what I'm not mentioning here is the fact that due to the fact that we're modeling, we're starting this modeling by some statistical consideration on the form of the PDF, there are also some hyperparameters involved in the expression of this model, and I'd be addressing this topic in the following. So far you don't see them, but of course they are there, and I will talk about that in the following. So as the title of my talk suggests, the starting point is going to be very popular, very well-known and studied regular image regularization model for imaging inverse problem, which is total variation regularization, which I'm writing here, and I'll consider in the following in its simplest form, which is in a purely discrete setting, where we are just basically considering the sum of gradient magnitudes over n pixels, where n is the size of an image domain. And here I'm introducing positive parameter alpha, which whose role is going to be clear in a moment. So I don't think I need to convince this audience on the reasons why TV is so popular. It has been studied extensively over the last 30 years due to its very interesting edge-preserving regularization properties, and combined to some standard data fidelity terms for noise removal problems and the blurring and so on and so forth. And from the point of view of optimization, TV is also particularly interesting because while being non-smooth is a convex regularizer, hence it is amenable for the development of efficient numerical algorithms. So the literature on review is really vast, so it's not going to be the topic of this presentation exploring all the different contributions for all the many viewpoints. I'm just referring here to some reviews or survey papers on the use of TV in different contexts. For instance, to some books in the context of imaging, to the book of Ambrosio Fusco Pallara for the study of TV in infinite dimensional setting, as well as the space of functions of bounded variation, and also to the recent review by Chambol and Poc for some very interesting examples on the numerical algorithms that can be used to solve TV-based imaging problems. And I will focus in the following also on some specific extensions on TV that I will highlight as we go on. Okay, so now I would like to start with a very simple example connecting the analytical expression of TV that I just shown you with the statistical world, let's say. And to do so, I decided to use this very common image that most of you have used probably in your experiments to validate your algorithms, which is the Barbara image. Why is that interesting? Because that's quite heterogeneous in terms of image contents. There are many homogeneous areas, and there are also some texture regions characterized by different properties and different geometries. And what I'm showing here is the histogram, nothing but the histogram of gradient magnitudes. And before I forget, let me just say that the gradient here is computed by standard finite difference discretization. So that's the discrete gradient. So this is just the histogram of gradient magnitudes. And now from here, we would like to understand a little bit more how can we relate TV to statistics, let's say. So the framework is also very well known and very well explored, which is the one of Markov random field modeling, and in particular the one of stationary Markov random field modeling, where the idea is to assume that my prior distribution, where now I am highlighting the dependence on some hyperparameters defining the prior and lying in a space which for the moment is intentionally left general, of course, but which will be made specific in the following, which takes this form. Okay, so there is some normalization constant, and then I have a negative exponential form where the quantities appearing here are called Gibbs potential, defined on some neighborhoods of each point I, called the click of the point. So what I'm saying here, the Gibbs potential is acting on the click and takes as input my image U, and its form, it depends on the hyperparameters that now are called theta. So what about TV? For TV, I'm taking discrete gradients. So for each point I, which I'm here color coding in red, I'm considering the 3 points in the computation of my gradient. So we have to think about the Gibbs potential to have this form, and together with some parameter alpha, which is the one that I introduced before. What does it mean in practice? What we are saying here is that for each pixel I, if we look at the gradient magnitude evaluated in the point I, we can say that this is then a random variable distributed by as a univariate half Laplacian distribution, where univariate is due to the fact that it's a scalar random variable. The fact that it's half Laplacian is due to the fact that we're looking at norms so that the value are non-negative. And alpha here then is has to be intended at the as a parameter defining the shape of my half Laplacian distribution, and plays here the role of global image scale. Let me explain this a little bit better. Let's go back to the histogram of gradient magnitudes I showed you before. And what you see here is the fit of this empirical histogram by a half Laplacian distribution where the parameter alpha has been estimated in an automatic way, as I will explain in the following. And we can do some consideration from this plot. We see that this fits the histogram quite well as far as the tails are concerned. The behavior is globally consistent with the one that we observed, but close to zero, we don't observe such a good fit. And remember, looking at zero here means looking at like the many points where my image has zero gradient, so mostly to homogeneous regions. So it was observed already some years ago and recently extended in a recent paper that the fact that this fitting is suboptimal is probably due to the rigidity of the PDF that we are considering in the modeling. What do I mean by rigidity? We have only one hyperparameter, the alpha hyperparameter, which seems to force my fit to a little bit too rigid and restrictive. So the idea that in these two papers was considered was to add 1 degree of freedom, in particular one further parameter, which corresponds in particular to assume that the gradient magnitudes are distributed now as half generalized Gaussian distribution, depending on 2 parameters. So now the alpha parameter I mentioned before, and a parameter P, which is a positive parameter, which is defining the global shape of my distribution. So in particular, in this work, some considerations on the case P smaller than 1 were done. That was called hyper-Laplacian distribution. And of course, it should be clear that whenever we take P equal to 1, we just retrieve what I presented you before. For those of you working on sparse optimization, that shouldn't be surprising, because if we then carry on with our derivation following what I've mentioned before, what you end up with is a image regularizer, which is quite similar to TV, apart from the fact that the gradient magnitudes here are have an exponent, which is exactly the p exponent I mentioned before. So it shouldn't be surprising that this choice of having exponents smaller than 1 provides, for instance, better fit of my histograms from the point of view of sparse optimization, because we know that whenever we move from a convex to a non-convex regime, and in particular consider some LP norms, sparsity is much more enforced. So that is just a nice connection, I think, to some recent work on the use of this type of image regularization models in the context of image reconstruction and image restoration. So, but let's go back at the statistical interpretation of that. So if I now do what I did before, so I just provide an automatic estimation strategy of the parameter alpha MP, which again will be detained in the following to fit my distribution. I see that this fit, the red one, is much better than the one that I had before. Okay. But there is still some limitation, and the limitation is due to the fact that when I zoom in some specific region, for instance here, characterized by texture, and I try to use basically the same fit of the distribution on this region, which is characterized by the presence of textures. Hence, we have large gradient magnitudes here, so not many points with gradient equal to 0 or anyway small. We see that the fit then becomes very bad. That's due to the fact that there are quite many points having large values of gradients. So this fit seems to work quite well at a global scale, but when we look closely at how to model local features, that doesn't seem to be a good choice. So analogous consideration can be done when thinking of describing in a statistic way some handcrafted prior, let's say, which could model the orientation dependence of my image regularizer to some specific orientation. In particular, for this synthetic image, which it clearly exhibits a dominant orientation, which is identified by the angle theta. We wonder how can we model, let's say, statistically and analytically also a regularizer that could adapt its shape to promote, for instance, regularization only along the direction of edges. So if you're looking at directional features, of course, thinking of gradient magnitudes doesn't sound like a good choice, because it's just a scalar value. So here, just for illustration, I'm simply showing the 2D histograms of gradients. You see a big peak in 0 due to the fact that the image is still piecewise constant, so many points have gradients equal to 0. And what you observe here is that, as you know from standard analysis books, you see that the gradient here is oriented perpendicularly to the level line, so in particular to the direction theta that I've written here. So there is a clear dependence on the gradient on the edge direction. And how can we model these? So the first idea is to then look at some prior distribution acting locally on the gradient and not on its magnitude, assuming in particular that this quantity locally is distributed as a Laplace distribution defined in terms of a covariance matrix sigma, which is a 2 times 2 matrix, hence SPD, SPD matrix, hence invertible, so that this is well defined. So here I'm not writing the constant because I want you to focus on this term, but I will make them precise in the following. And in particular, I show you in the next slide that sigma codifies global scale and orientation features. How can we see that? It's pretty easy actually, because since sigma is a symmetric and positive definite matrix, we can diagonalize it in terms of orthonormal matrices. So we can define, say, a diagonal matrix E and some rotation matrix V, so that this term here can be rewritten in a different form, where you can convince yourself, after some geometrical considerations, which are pretty obvious, that the rotation matrix appearing here really relates to the orientation theta of the edges that I introduced in the previous slide. And what you have here is a diagonal matrix which depends on a parameter A, whose range is 0, 1, with 1 included, which has to be interpreted, as I will detail in the following, as a sort of anisotropic matrix, whose, in particular, the value of A will change the shape of my distribution to be strongly anisotropic, in particular when alpha approaches 0, to fully isotropic, the first case being the one related to favoring regularization along theta, and the second being the case of fully isotropic distribution. Okay, so now we can then use this form for defining my prior. And let me point out, in terms of number of parameters, that since sigma is a SPD matrix, 2 times 2 is defined in terms of 3 parameters. So here we are just introducing different parameters, but the dimensionality has not changed. And we retrieve this form for the regularizer. And it's quite interestingly, that relates to some nowadays popular image regularizer, in particular the one of that has been introduced first in 2012, but by Raman Kamasak, under the name of directional total variation, and then extended more recently to the continuous framework by Ichudong and co-workers. So let me point out again that both the orientation theta here and the other parameters are still global. So this regularizer has been shown to work quite nicely in the case of images with global directionality. Which is not like what we observe in practice in most of the cases, of course. So as a geometric interpretation and comparison between TV and DTV, so here I'm fixing the alpha to 1 just for simplicity. We can consider like standard duality arguments and do some interesting geometrical considerations. In particular, by duality, we can write this norm, this norm appearing here as the max of this scalar product, where the test functions lie in the unitary ball of centered in the origin. And after some standard manipulations, you can show that actually in the case of DTV, what you get is that the scalar product is maximized over the set of the test functions which lie in an elliptical region defined here, characterized by the fact that theta then represents the orientation with respect to the x-axis, while A denotes the length of the minor semi-axis. So here I'm just showing you some geometrical considerations on that. You see in black the unitary ball, in magenta the elliptic region with different values of A, the value A equal to 1 corresponding to fully isotropic behaviors like a circle. And as A reduces, we see that the ellipse shrinks to a line. And I'm not sure you can see this, but like the arrows color coded in magenta are the ones realizing the maximum here. So we see that in the case of isotropic shape, it aligns with the gradient, so that we get back TV. And as the ellipse reduces, so the parameters A reduces and shrinks, so the ellipse shrinks to a line, this gets aligned to the direction V. So we can say that formally, basically, if we introduce this quantity, which are the directional derivative along theta and its perpendicular weighted by a, we have that this dual function optimizing the scalar products aligns with V. And actually, dTV can be written then in this form. Okay, so I don't think it's hard to convince you that, of course, thinking of images with global and dominant direction is pretty restrictive. If we look again at the Barbara image here I'm plotting the histogram of the whole image. So we see there is clearly no global directionality. And if we look closely at some patches, well, of course, we have different dominant directions depending here, for instance, on the sort of behavior of the texture. While, of course, in the case of homogeneous regions, we don't have a clear directional preference. So it's still a bit restrictive, not allowing these local features to be defined at each point in a different way. So before I move to the second part of my talk, then let me say that combining everything I said so far, we could also think of defining a different prior distribution on local gradients where all these parameters, so the scale, the shape, and the directional features are encoded at a global level. And it takes this form. So of course, the case p equal to 1 is the one that I mentioned before. And that's the sort of corresponding dTV-P regularizer that you would consider. So now, let me try then to define analogous regularization models where then the dependence on local quantities is made precise. So statistically, how should we interpret these? Well, the framework is again the one of Markov random fields, the difference being that the Markov random field is not stationary anymore. And what do I mean by not stationary? I mean that the hyperparameters appearing in the definition of my potentials do vary depending on the point. So here the space that was before indicated by x is now space x to the n, because for each pixel I have theta I parameters lying in the space x. So of course it's a very large dimensional space. So the idea is actually pretty straightforward if we want. So the idea is that to start again from the basic statistical assumption that we had on graded magnitudes, which ended up in TV, and assume instead that my graded magnitude is locally distributed as a half Laplacian distribution, and the local parameter is alpha I. So it depends on the pixel I. Hence the set of hyperparameters as the same dimension of my image. So if you do this assumption, what you can do is simply follow again the same strategy that I detailed in the first slides and derive this weighted TV regularization, where basically now the scale parameter alpha I is a local parameter, so it cannot, of course, go out from the sum. So interestingly, the use of weighted TV regularization models is nowadays used in several imaging applications, and it has been explored from different point of view. For instance, from the point of view of analysis in functional spaces, from the point of view of structures of solutions, and also applied to several imaging problems, where the idea is that for each point, of course, you can tune the amount of regularization that you get. Okay, so by proceeding in a similar manner, we can then define the dTV-P regularizer that I defined before at a global level by simply allowing the parameters defining its distribution to be local, so to change at each pixel. And now the space of hyperparameters is really, really large, but we have a clear interpretation, at least in terms of their PDF of what these parameters represent. So this is the resulting model that we end up with. So the notation here is a bit complicated to follow possibly, but as I will mention in the following, in different contexts, analogous regularization models have been called under different names. So at some point we had to make a choice, and in order to highlight the space variance, space variant modeling, we decided to add SV here, and also to highlight in bold every quantity which is not a scalar but just a vector. I'm saying that so that maybe it's easier to follow. Okay, so as I said, the use of space variant models in imaging is not new, but while preparing this work, we realized that it has been called differently from different communities. So, for instance, in the statistical community, as I said, these ideas are really related to non-stationary Markov random fields, and you will see in the following also to hierarchical optimization approaches. As far as more classical imaging models, for instance, inspired by PDEs, the use of space variant directional information should ring the bell and let you think to anisotropic diffusion models or more recent extensions to structured tensor TV regularization. As far as the exponents, so the PI are concerned, the use of variable exponents even in infinite dimensional setting has been proposed in some previous work, where the idea was to adapt the value of the exponent closer to 1 in correspondent of edges and closer to 2 in correspondent to areas where you want to favor diffusion. Let me say that there are also very recent extensions to directional total variation models to higher order TV type models with some analysis and applications. And as far as applications of these space variant models are concerned, we found that they are often referred to as structural regularization models for quite a variety of medical imaging problems. For instance, MRI, joint PET MRI reconstruction, computed tomography, and so on and so forth. And also, as far as the numerical discretization of this model is concerned, let me say that there is, of course, some work on how to discretize your gradient and diffusion operators in a way that is adaptive to your directional information and features at the point. So regarding some comments on the flexibility of this distribution, what I'm showing here is just some simple plot on why you should be convinced that these distributions are indeed more flexible. In particular, this one, where you see that for different values of P, you range from very steep and very peak distribution to distributions which correspond to the uniform distribution as P go to infinity. So it's better adapted to model locally the shape of your gradients. As far as two bivariate distributions are concerned, we see here some further examples where, for instance, you have here an example where the anisotropy parameter is equal to 1. So what you observe is that your level lines are fully isotropic, but due to the fact that P is smaller than 1, your distribution is very peaked. And here, if you change, for instance, your parameter A, and you let it go approach 0, you get something which models much better the local anisotropy preference that you may want. Okay, so now I've talked about this hopefully interesting modeling, but I've also highlighted the fact that it depends on parameters like in a very high dimensional space, because for each pixel, I'm thinking of describing local features with up to 4 parameters. So how do we estimate those parameters? So if we go back to the bias formula that I mentioned in the first slide, what we can write is, in fact, we can keep the explicit dependence of these parameters and do one more step here by introducing some, by applying the rule of conditional probability. Here we can introduce some prior on the hyperparameters. So we will refer to it in the following as hyperprior, which may model some prior belief that we have on their values. Hence, here we end up with a joint posterior. And so we can think of optimizing with respect to U and the hyperparameters at the same time, so that we look for a pair. Now, to solve this optimization problem, Daniela Calvetti and Erkki Somersano have proposed some years ago to use this iterative algorithm called iterated alternating sequential IAS algorithm, which starting from U0 alternate the minimization between minimization over the hyperparameters and minimization over U. So in the following, we will be inspired to this algorithm, although I will clarify which modifications we introduce. And let's focus then on this step, which is the one corresponding to the estimation of hyperparameters. So if we focus on this step, then we need to make we need to introduce a suitable hyperprior. So there are several choices for that. But at a macro level, what we could have is that we could introduce an informative hyperprior, which means introducing some prior belief that we have on the parameters, or, and this is the case for what will follow, in order to keep things simple, at least for this moment, just imagine that we don't have any intuition on the hyperparameter values, so that we use a uniform distribution and a uniform hyperprior then, possibly improper hyperprior in the case the space is unbounded. Okay, so now let's go back to the computation. What is important here is that if we introduce a uniform distribution, we have then a scalar quantity here that does not depend on theta anymore. So the only thing that matters really is the space where these parameters lie. So if we now compute this negative logarithm of my conditional prior. In the case of weighted TV, for instance, we have these computations where we I highlight the fact that we carry on the hyperparameters involved, which in this case is simply the vector alpha, and we also have the normalization constant, which appears in my prior, and I will comment on that in a moment. So just to say, we can do the same also for the more general regularizer that I denoted by DTV-P. Where again you have a quantity depending then on the hyperparameters and then the normalization constant. So okay, so what we did to estimate those parameters was to consider an approach which is related to standard maximum likelihood, but which approximates these because a little bit artificially does not compute and does not take into account this constant Z. So the statisticians in the audience, of course, won't be happy about that because that's the crucial and the most challenging part in maximum likelihood estimation approaches of hyperparameters. The fact is that this constant is often very hard to compute in practice. And in our case, the issue is that we even have to iterate this computation because this is part of a sequential algorithm. So just to see if our estimation idea worked well, we decided to use an approximate maximum likelihood approach, where the idea now is okay, if we forget about this constant, we see that this problem is separable. So we can look at the optimization of one single component. And if we impose optimality here, we see that for each parameter, the corresponding alpha I will be depending on the local image gradient magnitude. So in the case of noise and blur, this may be an unreliable estimate. That's why we prefer to use this maximum likelihood type strategy, where the idea is that for each point, we define a neighborhood of some fixed size, and you suppose to sample in this neighborhood from the very same distribution you want to estimate the parameter over, so that what you have here is a product of prior distributions defined in the neighborhood, so that finally you end up with this optimization problem to solve. And it's quite nice to see that it admits a very efficient and nice closed form, the solution, because for each I, what you do then to select your local regularization parameter is simply to take some average of the gradient magnitudes around that point. And in order to avoid to divide by 0, we introduced like a very small parameter epsilon. Clearly, this can be done very efficiently from a numerical point of view, for instance, by computing convolutions by DFT. So if we then look at the behavior of this estimation procedure on a well-known test image, which is the one of the skyscraper, we see that, again, those are the two histograms computed on the global image. But if we look at patch, if we see, if we compare here the two fits, the green one being the one corresponding to the global fit, the red one being the one to the local fit, we see that this local alpha estimation is much more precise. Here in particular, we have an homogeneous region, so we want to have something extremely picked. In the case of texture regions, we see that the local estimation still adapts the shape of my half Laplacian PDF better to the contents. But as I mentioned before, it's still suboptimal due to the fact that we still have some rigidity due to the shape of the prior that we are assuming, which despite the fact that it's changing its parameter, is still a Laplace distribution. So, okay, without going into the details, what I'm saying here is that we could do the same also for the more complicated models, for instance, for the fully space variant model. And you end up with the functional define here. So for that, we can still find an explicit expression for the weights alpha I, and we need to reformulate on a compact domain the problem in order to guarantee the existence of solutions. But this is like not artificial as it sounds, due to the fact that anyway, when we want to estimate these parameters via our laptop, we should fix anyway some bounded interval and compact too. So to do so, we use some standard interior point solvers. And let me say on the fact that this estimator is not really ML, but is very close to ML, that in our previous work, we showed some empirical results proving the fact that is an unbiased estimator on some simulated example, and which also had good accuracy properties. Okay, so I'm quickly moving toward the results. This is just to show you some estimation of parameters of my distribution on very simple and synthetic examples. So here I'm looking at the shape of distribution for points on the edge. So you see here that by using this ML approach, the parameters that I estimate correspond to the framework that I discussed so far, because theta here is the direction of my edge. And I have a very picked distribution too, because P is very small, because I really want to stay sharp in my local content. Same here. And also same here when we look at points lying on the circle. Here we see that again, the angle estimation is quite precise. And when we look at texture context, the estimation becomes, of course, much more interesting, because if we look here at the configuration of the gradients, this is much richer than the ones that I showed you before. And this is basically the fit with the estimated generalized Gaussian distributions with these parameters. And so we see that the samples fit quite well with the estimated PDF. And same here, where there is some more directional dependence due to the fact that the texture is much more geometrical than the one before. And we do see that here. Okay, so now the question is that, can we use this modeling to improve upon some limitations and some rigidities of TV image regularization models due to this combined parameter estimation and space variant image regularization modeling? So before showing you the results on that, I need to make specific some more information on this step, so on the solution computed with respect to you, particularly on the likelihood, because I haven't mentioned which type of noise we will focus on. So, okay, for simplicity, I decided to report just examples corresponding to additive realization of Gaussian noise, so that the likelihood looks like this. And by taking the negative logarithm, the fidelity term that you end up with, the standard square norm of the difference between KU and F, depending on some parameter U, which appears due to the fact in connection, let's say, to the variance sigma squared that we have here. So to estimate that, we will use in the following discrepancy principle. Let me comment that whenever you have a global image regularization model, you can, and this is what you do in practice most of the time, I believe, you basically can divide the hyperparameters of your prior by this hyperparameter U, or vice versa, so that you end up only with one regularization parameter. But in the case of space variant modeling, due to the fact that those relates really to the descriptors of the local PDFs, we prefer to keep things separated, but still having an automatic selection strategy for that. And let me say that this generalizes also to additive and more general type of noise, for instance, Laplace and uniform noise. Okay, from the point of view of optimization, then we want to solve this optimization problem, which is non-convex in general, due to the fact that depending on the values of pi I, you are not sure about the convexity of your model. In particular, whenever at least one pi I is smaller than 1, you don't have a convex model. We can show existence of global minimizers, and of course uniqueness in case the pi I are all greater than 1. How to solve this? We decided to use Adm optimization. The fact is that we are not sure about the regime of this regularizer, because of course we could think of different and maybe more tailored numerical algorithms addressing situations where you have smoothness and convexity, but in order to keep everything quite general, we prefer to stick with Adm optimization with this variable splitting. So I just go a little bit quick on the details, because basically those are just the iterations, and some of them can be solved quite efficiently. Here on the minimization, the sub-problem with respect to R, you also enforce your discrepancy. What I think is maybe the most interesting one is the step involving the possibly non-convex term, which is a sort of non-convex proximal step. We cannot hope for an explicit expression, but what we showed is that we can anyway simplify this optimization problem, reducing it for each component, each gradient component, to a one-dimensional constraint optimization problem, which simplifies the computations. Okay, so that's the whole pseudocode of our model. Let me point out that differently from what I've mentioned before, the update of the hyperparameters here is done inside the IDMM iterations. and not as a separate optimization scheme. Why that? Well, the IIS algorithm I've described before does not have in general convergence guarantees in the case of non-convex modeling. But it's of course much more demanding because it requires to perform the estimation of parameters at every outer iteration step. Whereas while embedding these here seems a little bit artificial, given the fact that we are still in a fully non-convex regime, so convergence is still an open problem, we could at least gain something from the point of view of computational efficiency. Okay, so let me just show you some results to conclude. I probably skip these and simply show you the resulting images. So those are just some comparisons between standard TV image deblurring and the other models that I described before, where the parameters have been estimating following the same strategy, ML type strategy discussed in the previous slide. And you see here in particular that when you use your fully space variant model, you get some improvement in terms of texture preservation. So here are just some tables confirming this, but I think I'm running out of time, so I quickly move to the final example again on the skyscraper image. Those are just the global reconstructions that we get, and those are just some zoom on some specific regions. So here we see the typical staircasing of TV, which is reduced a lot in the case of radio-weighted TV, and even more in the case of directional TV. And here the texture part in the case of space variant models seems to be better preserved than TV, as we expect. Okay, so I just skip these two slides and move to conclusions. So the main message of this presentation was somehow to unify the many contributions that have been done over the last year on space variant models for improving TV reconstruction from different viewpoints, and in particular providing it with a sort of statistical interpretation linked to the use of space variant bivariate generalized Gaussian distributions. Characterized by some local features, in particular scale, sharpness parameter, and directional behavior. And this, I found this particularly interesting because by exploiting the statistical interpretation of these, we could even come up with some interesting parameter optimization and estimation strategy, which resulted in a highly parametric and non-convex optimization problem, which opens many questions. The first one would be to use some more informative prior. Also, proving convergence for the non-convex ADM scheme remains an open question, as well as also defining some more appropriate discretization stencil. Let me just advertise the fact that this presentation was based on a quite extensive review paper that we are currently proofreading, so it will be submitting in the following days, hopefully. And you will find there all the details and also some extensions, for instance, to non-Gaussian noise models. I conclude also providing a short list of relevant work that we had on these. And with that, I thank you all for your attention, and I'm happy to take questions.
Thank you, Luca, for this very interesting talk. So now we are open for questions. I have already one question in the question and answer box, but I don't know if Côte, you want to ask it for yourself, so you can speak.
Yeah, I can ask it if you want.
Yeah, please.
Thank you very much, Luca. Very nice talk.
Thank you.
So my question is about the regularity of the function theta. So if we think of the function space setting, for example, for the weight function alpha, you will need a certain regularity for the weighted TV to be well defined, for example, continuous weights. Do you have any idea what kind of regularity would you need for theta in the function space setting? Or in general, how does it look like in the numerics, like piecewise constant or something?
no, I don't have a clear answer to that. Also, the estimation so what I maybe didn't make precise enough is the fact that there is anyway some dependence on the sort of window where you estimate your parameters. So in the numerical experience, this is something that has to be chosen with some heuristics and which may result in differences. So it's hard to answer on guess which sort of regularity you would like. No. But I mean, the study of all these in functional settings is also part of like the open problems. We decided to start in a fully discrete one, mostly because of the presence of these exponents that may be smaller than one, so that the analysis in function settings we thought could have been very complicated. So we didn't think too much about the regularity of the others, but it would be interesting to see that. Yeah.
Thank you very much. Yeah.
Thank you.
Okay, so we have the next question from Jonathan Whitmer. Jonathan, you go ahead.
Yes, so of course. Yeah, Jonathan is asking about the cost of solving these in the full space. Yeah, that's of course something that is a bit different from TV because, let's go back to the algorithm. Sorry, it was here. Okay, so so the general answer is that it really depends on which sort of generalization of TV you are considering. In the case of weighted TV, since the expressions of the ith parameters is in closed form, that's really efficient. So you don't lose much in terms of computational costs. Of course, when you think of estimating the whole set of parameters, that's quite demanding. So that's also why, although this is nested inside the ADMM to further improve efficiency, one possibility and something that works quite well in practice is to estimate these not at each iteration, but every few iterations, so that you do these updates every, I don't know, 30 iterations. So just to tell you, I think for the fully space variant model, maybe this step could take kind of a minute. So it's of course demanding.
Okay, so we have a question from Côte. Manny.
Oh, hi. Interesting talk. Okay,
hello.
I have two questions. One is from the, I have experience using like union of subspace type approach for similar problem, right? So because one union of subspace, you can use a harmonic, a basis that is sort of like good for harmonic component that would sort of tackle the texture region well. And then you have another set of bases that are more edge, good for modeling edges and other singularities, right? So that is sort of like my, a kind of global point of departure. The other is that, like in the Markov random field, you talk about the clique, and to me, that's non-local means, right? Non-local means basically say, we want to find patches or pixels that have similar neighborhood, and then we do our optimization or do our magic within that, right? As opposed to do it globally. So I like the fact that you try to do spatially varying and very sensitive directionality. I think that's key, which is the weakness of original total variation. But I think solving it per pixel seems very heavy lifting.
Of course.
So I wonder whether we can use the self-similarity idea and kind of like pre-sort the patches based on a patch similarity or pixel similarity, and then solve your estimation problem within there, in which the patches are already more similar, hence more likely to be from the same distribution. Yeah, thank you. The other one is the fixed point issue of your algorithm. Does it converge? What is the fixed point convergence to? Anyway, thanks.
Yeah. Okay, so I start from the second one. We observe the empirical convergence, so we cannot say more. So something more from a theoretical point of view needs to be rigorously proved. But in practice, upon suitable initialization, which is also a question, of course, because we are in fully non-convex regimes, we get good results and empirical convergence to some fixed point, some stationary point. So regarding your first comment, which is much more interesting, of course, we should exploit a little bit more similarities, and that's also, I believe, will be key. What I think was really the message here is rather to introduce some statistical interpretation of these regularization models in terms of some hyperparameters associated to their PDFs. And then just to test whether this was like a good modeling, we decided to test and come up with some very heavy optimization. But of course, something more clever could be done and should be done, probably knowing at least now how these distributions look like. So yes, totally agree.
Okay, the next question is from Stacy 11.
Did you want me to ask?
Yeah,
sure.
you can go ahead.
Really interesting talk, Luca. Thank you. I was just wondering, it looks like the corners are really well preserved with the DTV. Is that something that's quantifiable or that you've looked at? I know some of the work at Bill Allard and some of his collaborators have done that for TV some years ago.
You're talking about some specific image, or maybe?
I looked at just the one with the buildings. It looked.
Yeah. So yeah. The thing is, like the estimation is pretty precise in terms of angle. So that's the good thing. Regarding the comparison, we didn't compare, for instance, with other approaches for estimating directions of based, for instance, on structure tensor or something different. What is the approach again that you mentioned for comparisons?
It was just some older work by Bill Allard and his collaborators, where they were looking at what happens to corners, how when it undergoes TV processing, and how the corners bend, and they actually quantified how much you lose the corners. The simple answer. Just wondering if you had looked at anything.
No, we haven't, but would be very good to check on that. One other thing that I can say is that, as I said very quickly at the conclusions, right now I believe that there is room for improvement from the point of view of numerical discretization, because right now we are estimating parameters, but then the gradient that we compute is still like a forward difference, like on the standard grid. Whereas I think it would be very interesting to use some ideas from adaptive stencil from anisotropic diffusions to improve. To incorporate the information that you get in your discretization itself, because that would be maybe even better for very anisotropic structures or edges or corners.
Okay. We have many questions. The next one is from Daniela. Daniela, please.
Okay. Luca, thank you for your talk. Very, very interesting. And I have a quick question. Since the problem you are solving is non-convex, I'm just wondering if you observed any sensitivity of the computed solution on the starting gas.
Yes, of course. Yeah, yes. So we have now found a good initialization, which seems to work quite well in practice and for different situations. So I didn't have the time to detail, but is based. So the idea is to somehow solve a simplified convex problem first and get these as your initialization. What we were doing before was initializing by solution of, for instance, TVL2 problem. With parameters selected, for instance, with discrepancy principle. What we're doing now is something similar, but where the parameter is selected by using some different strategy. In particular, it's minimizing residual whiteness. So, and that seems to be quite robust. So, of course, that's an issue, though. So, if you start with, we tried with you know, starting with zeros, and that also changed the result. This last one seems to be quite nice because differently from the TVL2 initialization considered before, does not oversmooth too much structure, so that we see we don't estimate wrong parameters since the beginning. We somehow have already a good estimation that is improved.
Okay, so in practice, this means that you are getting closer and closer to your results with this new technique, with this new strategy in some sense.
Yeah, exactly.
Okay, thanks a lot.
Thank you.
Okay, any other questions? Yeah, we have a very lively discussion. Okay, so
thanks a lot.
we are already one hour of time. Okay, so maybe then we thank Luca again for this very interesting and exciting talks, and I hope to see everyone next week and on Wednesday again. Thank you very much.
Thank you very much,
Luca. Thank you.
Bye.
Great
Thank
talk.
you.
Thank you.
Thank you.